Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to sketch graphs in polar. We're going to take a look at what we're going to do here is we're going to try to sketch a graph of r equals cosine theta in polar cylindrical coordinates. Now, a very important tool, or a very good tool I should say, for graphing in polar is to start with a Cartesian graph. So the very first thing I'm going to do is graph r against theta for this function, and again it's going to be a Cartesian graph, so that's standard like xy type of coordinates. So a cosine wave starts at the point 0, 1, looks something like that. That's one cosine wave. I think that's all I'm going to need for this graph, and of course it keeps going on forever in this direction and forever in this direction. Some important points here, right? So the cosine function goes through the point 0, 1. Here's another important point. That's the point pi over 2, 0. This is the point 3 pi, pi minus 1, 3 pi over 2, 0. And this would be the point 2 pi, 1. All right, so now what we're going to do is I'm going to use this curve to try to sketch a curve in polar for r against theta. Now, we're going to take a look at this curve here. The first point here goes through the point 0, 1. In polar coordinates, an angle of 0 is along this axis. So the point 0, 1, actually in polar, some books write the point 1, 0, would actually be over here somewhere. So I'll go ahead and do this. I'm just going to leave this in green. So in polar coordinates, this is the distance 1, angle of 0. Now I know it looks like it's the point like 1, 0 in Cartesian, but that's actually a polar coordinate. This is a radius, that's 0. Now, on this curve, again going back to my Cartesian graph, as our angle goes to pi over 2, the radius decreases. So as we follow along this curve, r gets smaller and smaller and smaller, and we're looking at these vertical distances now, and it goes to 0. So up on this graph, our radius is 1, but as the angle increases, the radius has to go to 0. So a decreasing radius is going to look something like that. And again, important thing to recognize here is this distance is decreasing. Over in this graph, that's these radii here, decreasing and hence going to 0. Right. Now, as we break through pi over 2, first thing to notice is the radius now becomes negative. Basically in polar, that means that you are going in the opposite direction. Now you notice that the radii are negative everywhere in this region between pi over 2 and 3 pi over 2. So going to my polar graph, right, this angle is pi, right there. And then to here, that's 3 pi over 2. So when we are in this region, the radii are, I'm sorry, I was talking about the wrong region here, pi over 2 to pi. So pi over 2 to pi, so pi over 2 to pi. When we are in quadrant 2 here, the radii are negative. So those are actually going to fill out values in quadrant 4. Right? So I'm going to do this in a different color here so I can kind of code this. So from pi over 2 to pi, the radius goes to negative 1. So pi over 2, starting at 0, the radii are negative, and going to negative 1. So that's actually going to do this. And that's going to correlate to this part of the curve, to that point right there. So again, you notice that pi over 2, the radius is 0. That's this point right here, angle of pi over 2, radius 0. And then think about, an angle like pi over 2 plus some sort of small, like maybe 0.1. So pi over 2 plus 0.1 moves us just a little bit down on this curve. We'd be maybe here, right? Pi over 2 plus 0.1 is just slightly to the left of that, the vertical axis here. But the radii are negative, so that point is actually about here. And then as we move further down, that radius is increasing, going to 1. And in this picture, radius increasing, going to, now I know it's negative 1. The minus sign means we're over to the right. Actual distance is 1. So if we keep going with this graph, this part here is just going to repeat itself. The radii are negative and going to 0. Now you'll notice that this angle was between pi and 3 pi over 2. So that's again over here in quadrant 3. The radii are starting at -1. That would actually be here. And going to 0. That would actually just kind of overlap and fill out another part of the curve. So what we've done here is we've already filled out the graph, and it's basically done. Now this is meant to be kind of a rough sketch, and as we take a look at this and we think about the shape here, it kind of looks like a circle. I'm going to go ahead now and just fill in. This is kind of a nice color for this. So the entire graph here, I guess kind of uncolor coded, is looking something like this. It's looking circular. We might guess, is it perfectly circular? And I'm going to kind of investigate that by shifting this over to Cartesian and looking at the equation for it. So I need a little bit of room. All right, so we're going to take a look at this. R equals cosine theta. And going back and forth between polar and Cartesian, remember the relationships, there's basically 3 important to know. X is equal to r cosine theta, y is equal to r sine theta, and Pythagorean theorem is r squared equals x squared plus y squared. So if I take this equation here and I multiply both sides by r, it's now going to read r squared equals r cosine theta. Now, r squared is equal to x squared plus y squared, and r cosine theta is equal to x. This now we can move to the left. And you'll notice that this equation is starting to look like the equation for a circle. Now, the equation for a circle in standard form is x minus h squared plus y minus k squared equals r squared. We can make this look like this by completing the square on this x term here. So hopefully we're kind of familiar with completing the square. The purpose of the video is not how to complete the square. I'm just going to go ahead and do it. This term I can turn into a perfect square by adding 1/4 to both sides. So this is going to look like x squared minus x plus 1/4 plus y squared equals 1/4. The 1/4 is when you're completing the square, you look at the number in front of this, which is a 1, take half of it, which is a 1/2, and square it. This now, by design, is equal to x minus 1/2, the quantity squared. This, we could leave alone. I'm going to go ahead and write it y minus 0, the quantity squared. And then the right-hand side is 1/4. So when we compare this to the equation of a circle standard form, you'll notice the h is 1/2, and the h is the center coordinates of the center. The k is 0, and the r is 1/2. So this is the equation for a circle centered at the point 1, 0 with a radius of 1/2. So that's exactly what we're looking at right here. I'm sorry, I think I said 1, 0, 1/2, 0. So the center of this circle is the point 1/2, 0. It has a radius of 1/2. That means this point right here would be the point 1/2, 1/2. This point would be 1/2 minus 1/2, and so forth. So I just went through the second part here to kind of confirm that my geometry was in fact looking circular, and it is. So I hope this video helps demonstrate how to use a radius graph in Cartesian coordinates to sketch a radius against theta graph in polar. Have a great day.